Okay, so we can start now. Maybe can you share the screen?
Yes, of course. Do you prefer to turn off the camera or
As you wish.
what's better? I don't know. I don't know if
No,
my
I think you can keep the camera. It's fine
okay.
because and some people are joining via YouTube, so they can see.
Okay. Now you see my screen. You see the presentation.
Yes, but yes, okay. So welcome everybody to this week's Majorana-Raychaudhuri seminar series. We are happy to host Apostolos from ETH Zurich, and he's going to talk about cosmological phase transitions and electroweak baryogenesis in the standard model and beyond standard model. So maybe I will send you a reminder when 5 minutes are left.
Okay. Thank you very much. Thank you very much for the invitation. Hello, everyone. I would like to mention that some minutes ago I had some problems with my connection. So in case my connection is very unstable, I will turn off the camera. First of all, I would also like to thank the organizers for this initiative. It's very interesting to organize and have this seminar series on high energy physics. And today I'm going to talk about cosmological phase transitions and electric baryogenesis in the Standard Model and beyond. And we are going to start with an introduction to the problem. Why do we care so much about electric baryogenesis? And the problem is that during the early stage of the universe, matter and antimatter were expected to be produced in equal amounts. However, in contrast to our experience, the observable universe mainly consists of matter, with almost no evidence of antimatter. Thus, how can we explain this inconsistency or contradiction in our theories? And one of the most promising solutions or descriptions of a process that we start from an early universe with matter and matter in equal amounts, and we end up in a universe with almost no evidence of antimatter, is electrobaryogenesis. So we want to describe this process, which seems from the very beginning as a phase transition. It's not exactly a phase transition, but yeah, it's a physical mechanism in the early universe that generates an asymmetry between baryons and antibaryons during the electric phase transition. Of course, there are other different models or different solutions to the problem of baryogenesis, but I think this is the most promising and widely accepted solution, which is called electric baryogenesis. Sakharov imposed three criteria so that this asymmetry between baryons and antibaryons is established. The first criterion is the baryon number violation, the second one, the CCP violation, and the third one, the departure from thermal equilibrium. I stressed, I will focus a lot on the last two, especially the third one, because these are not consistently and fully described in our theories, especially in the standard model. And the third criterion is often translated into a criterion for a strong first order phase transition. So the third criterion is satisfied if we require that in the early universe there was a strong enough first order phase transition. However, what is a phase transition? What is a cosmological phase transition, such as the electroweak phase transition in the early universe? A cosmological phase transition is a macroscopic cosmic event And intuitively, you think of it as a phase transition at large scales, at cosmic scales. But it's a phase transition so violent that can cause the formation of topological defects, the generation of the baryon symmetry of the universe that we are interested in today. And it can also generate a gravitational wave background, or better to say, to be more precise, during this phase transition and after, there's a generation, a stochastic gravitational wave background is generated. And Linde in 1978 noticed and wrote something that I found very interesting, that the phase transition, I mean, this is a very well-known fact, but it's a very nice connection to how phase transitions occur in cosmology, in the universe. So a phase transition is a process that involves a symmetry that is spontaneously broken before or after the phase transition. Therefore, it is obvious that the electroweak phase transition is a cosmological phase transition associated with electroweak symmetry breaking, which is an essential ingredient for the formulation of the standard model. But first of all, what is spontaneous symmetry breaking? Probably most of you know that if a quantum field theory has a family of degenerate vacua, then the vacuum state of the quantum field theory or the system is degenerate. When one of these degenerate states is chosen as the vacuum state of the system, then the vacuum state will not be invariant under the symmetry transformation, because I skipped the beginning that first of all, we start with an action that is invariant under particular symmetry transformation, such as the standard model is invariant under the SU2 times U1 Gates symmetry. Therefore, when one of these degenerate vacua is chosen, the symmetry of the action is called spontaneously broken due to the asymmetric vacuum state. And formally, one could define the spontaneous symmetry breaking as the phenomenon in which a stable state of a system, such as the vacuum state, is not invariant under the symmetry transformation of its action, or Lagrangian. However, it is very common, especially at the master's level or when we introduce spontaneous symmetry breaking, to work to describe it using the classical potential, so we determine the vacuum expectation value of the scalar fields of the theory by the minimization of the classical potential. However, quantum corrections could change the vacuum expectation value and generate spontaneous symmetry breaking. Therefore, we would like to search and define, to search for a function and define it as a function that is minimized at the vacuum expectation value of the quantum field, including quantum corrections. And this function is called effective potential. Of course, to be consistent with the previous description, the effective potential should be identified as the classical potential at tree level. And at higher loop corrections or contributions, we write this form that you see in equation 1. Do you see my cursor?
Yes.
Okay. Because yeah, I will show equations, and I also have some figures. So this is the effect potential, which equals the classical potential in terms of a constant background field and the higher loop contributions to the effect potential. And the constant background field is defined as the vacuum, as the expectation value of the quantum field. Unfortunately, I won't have so much time to present further how you compute the effect potential. We're going to jump into the results. But before that, very quickly, a very simple example. When I have a Lagrangian of a self-interacting real scalar field, then the zero loop contribution, which is the tree-level contribution, corresponds to the tree-level potential that you see in 2, but in terms of the constant background field, phi c. And the one-loop corrections is the sum of all 1pi Feynman diagrams with a single loop and 0 external momentum. This is derived using the generating functional for connected Feynman diagrams and then for the 1pi diagrams. But I would like to explain further what the cosmological phase transition is, which is the core idea of this presentation. We know that the early universe was a very dense and very hot place to live in. So ordinary quantum field theory is not enough to describe quantum fields at these temperatures. Actually, ordinary quantum field theory describes elementary fields and their interactions in a surrounding vacuum at 0 temperature, like in particle colliders. On the other hand, if we want to model cosmological phase transitions driven by temperature, we need to extend the ordinary quantum field theory to finite temperatures and derive, ultimately, the finite temperature effective potential. Simply, and roughly speaking, the finite temperature field theory combines the ordinary quantum field theory with statistical physics. And this field theory, the finite temperature field theory or thermal field theory, enables us to compute the observables of the quantum field theory, such as vacuum excitation values, in the background of a thermal field, of a thermal bath, I'm sorry. Then, of course, we can, as I said, we can compute observables, the Green functions, and this is achieved by changing the time ordering prescription in our theory, using the imaginary time formalism or the real time formalism in the following. And in my research, I use the imaginary time formalism. And essentially, you simply introduce imaginary time to connect your ordinary quantum field theory with finite temperature field theory and introduce the temperature. I'm sorry that I won't be able to explain the details of finite temperature field theory. I mean, it's a very broad field. So similarly to spontaneous symmetry breaking, a phase transition is associated with an order parameter. In spontaneous symmetry breaking, we usually identify the scalar field as the origin or as the source of the mechanism that of the spontaneous symmetry breaking. So because of this very close relation between a phase transition and spontaneous symmetry breaking, it's very useful, especially in our case, to define the order parameter of the phase transition as the vacuum excitation value of the scalar field that is related to the mechanism of the phase transition. So this vacuum excitation value will allow us to distinguish the different phases of the system. The phase transitions, in general, can be classified into 2 kinds, the first order and the second order phase transition. In the first kind, the order parameter is a discontinuous function of the driven parameter, which is temperature, between the 2 phases. this is a very simple, I mean, it's not really a simple example, but here I computed the one loop final temperature effect potential in the standard model. Actually, in a way, this is the final result that I want to describe, but now I want to describe what the first order phase transition, and it will help me to use this diagram this figure that we will see later too. But the point is that the effective potential has this form, the blue, at temperatures higher than for example, 170 GeV. This is just an example. And at lower temperatures, we see that a second local minimum appears. And it's important to remember that the effect potential determines, to be more precise, the minimization of the effect potential determines the vacuum excitation value of the theory. So the vacuum excitation value is 0 initially at high temperatures. And while the temperature decreases, we see the formation of a second local minimum, which becomes degenerate with the previously global minimum. And that's how we often define the critical temperature as the temperature in which the degenerate minima have this, the temperature in which the minima, the local minima are degenerate. And we see in the next slide that at lower temperature than the critical temperature, so it's exactly the same effect potential, but now at different temperatures, we see that the second local minimum becomes global minimum. So from 0, it jumps discontinuously to a non-zero vacuum excitation value. The order parameter changes continuously with temperature during a second order phase transition. So we don't have, and it's important to note that here we also had a barrier, and here we don't have. It's an important distinction, and this also encodes the discontinuous behavior of the effect of the order parameter. So here, initially, at temperatures higher than the critical temperature, the form of the effect potential is this. And at lower temperatures, continuously from 0, it goes to a non-zero value. So continuously, it becomes the blue line. Now, a phase transition from the so-called false vacuum, which is the vacuum with 0 excitation value, to the true vacuum with a non-zero excitation value, proceeds via thermal tunneling. This can be better understood here, where due to the quantum and thermal corrections, we have a phase transition through thermal tunneling. So this is very similar to what happens in non-relativistic, in quantum mechanics, in textbook quantum mechanics, where we see that there's a tunneling phenomenon when there's a potential barrier. So it's very similar how the universe transitions from a vacuum with 0 vacuum expectation value to a vacuum with a non-zero expectation value. And this thermal tunneling causes the formation of the so-called bubbles of the broken phases, analogous to the bubbles in boiling water. So these bubbles are field configurations of the scalar field of the theory in the broken phase, which is defined as the phase with the non-zero vacuum excitation value, here, the true vacuum. then under certain conditions, the bubbles could spread throughout the universe to convert the false vacuum into the true one. So we are ready to understand the phase transition in the Standard Model, the most well-known, in my opinion, phase transition in the Standard Model, which is the electroweak phase transition, which is associated with the spontaneous symmetry breaking of the SU2 times U1 symmetry. And we have the electroweak phase transition that occurs from the symmetric phase with zero vacuum excitation value of the Higgs boson to the broken phase with a non-zero excitation value of the Higgs boson. So the Higgs boson is the scalar field associated with the spontaneous symmetry breaking in the Standard Model. And that's why the effect potential is expressed in terms of the Higgs field. More specifically, I adopt the common notation for the parameters of the Higgs three-level potential, as you see here, and it's the Higgs tablet, where phi is the Higgs boson. And if you recall what we said earlier, the three-level contribution to the effect potential is simply the classical potential in terms of the constant background field. So this is equation 6. And in my analysis, also in Beyond the Standard Model theories, we consider only the dominant contributions to the one-loop finite temperature effect potential coming from the gauge bosons, the top quark, and the Higgs and Goldstone bosons. The main reason is that the effect potential, you will see it later, depends on the effective mass squared, which depends on the mass. Zero. So here you see the Higgs mass, and we will also see the masses of the other elementary particles. And these are the most dominant because of their high masses and high coupling constants. Now, the take-home message here is that the dynamics of the electroweak phase transition, and in general, any cosmological phase transition, are described by the finite temperature effect potential in terms of the Higgs field, or of the scalar fields associated with the symmetry breaking. A technicality here to mention that the MS bar normalization scheme is adopted here to avoid the issue with infrared divergence that originates from Goldstone bosons in the OS schemes. And here you see the complexity of the effect potential. And here you see all these M's are the effective masses. And yeah, but here it's just to see, I'm not going to explain what's going on here. But this is the complexity of the effect potential if you want to consider to include the contributions of these elementary fields. And actually, I would like to mention that I also computed the effect potential for all the elementary fields, all the known elementary fields in the Standard Model, and it's true that the difference is negligible. So we're going to use this function here, this tool, to describe cosmological phase transition and their phenomenological implications. And for example, the previous effect potential can be plotted here. Actually, this is exactly the same effective potential to the one shown here. But I should clarify that here I vary the renormalization scale, which is introduced in the MS-bar renormalization scheme. And this is an important caveat, because in this analysis and in the mainstream analysis of the cosmological phase transitions, the effect potential and the thermal tunneling introduces certain theoretical uncertainties. One of them is the normalization scale. However, I'm not going to discuss this further. And in our analysis, this theoretical uncertainty is negligible. It becomes important if we want to model the gravitational waves generated from a phase transition, from the electric phase transition especially. And here you can also see that, for example, the effect potential predicts the same critical temperature for all these renormalization scales. By the way, it's important to mention that physically, it is motivated to choose the renormalization scale to be equal to the vacuum expression value of the Higgs boson. And okay, you see here a deviation of the vacuum expression value, but we care about the ratio of the vacuum expression value at the critical temperature divided by the critical temperature. And this does not deviate as much as you see here. So I will explain further what I mean by that, because electric baryogenesis requires a strong first-order electric phase transition, which is characterized by the following condition. So this is the condition that will determine whether the baryon symmetry of the universe can be generated during the electric phase transition. And this is also a parameter that appears further in our computations for the gravitational wave, for the stochastic gravitational wave background. Although I'm not going to present it today, maybe I will comment a little bit later. So this criterion is not satisfied in the standard model. You can see that. So I plugged in the values of the value of the vacuum expression value and the critical temperature. With the critical temperature is around 163 GeV, and this is less than 0.6. Therefore, the electroweak phase transition is not a strong first-order phase transition. And this drawback of the standard model motivates us to formulate theories beyond the standard model. So how can we satisfy this criterion to explain the baryon symmetry of the universe? And the simplest extension to the standard model that describes consistently electric baryogenesis is the singlet extension to the standard model. And I think this is a very appealing feature of this beyond the standard model theory, because it's the simplest addition to the standard model. And it's important to mention that I also consider the real singlet extension. And in particular, we extend the standard model by introducing a real singlet scalar field equipped with a Z2 symmetry. And the tree-level potential for the Higgs doublet and the singlet scalar field is given by this expression, where you see the tree-level Higgs potential that I showed earlier. And it's important to notice this interaction here with the coupling constant lambda HS. That will be very important later. So this effect potential is derived using a more general form and imposing the Z2 symmetry. And And the singlet mass squared is given by this form. And in general, I adopt the common notation for the parameters of the Higgs three-level potential. Now, we shall assume that a higher order operator of the single scalar field is coupled to the Higgs sector. And this dimension 6 operator originates from an effective theory active at an energy scale m. And this energy scale is of the order between 15 and 100 TeV. It's a new physics scale. And it is assumed to be much higher than the Electroweak scale, a fact that is further motivated by the lack of new particle observations in the LHC beyond the Electroweak scale. In general, it's important to mention that in the singlet extension, the parameter space is constructed by the 4 parameters that I showed earlier, where lambda is the Wilson coefficient introduced in the dimension 6 operator. And for the numerical results, the effective theory is considered to be active at an energy scale around 15 TeV. Then the parameter space is mainly constrained theoretically and experimentally by the vacuum structure, the perturbativity of the couplings, and experimental constraints for the invisible Higgs decay width. If we further require a strong electron phase transition, then the parameter space is further eliminated by the criterion that I showed earlier regarding the ratio here, that it should be higher than 0.6 or 1.4. Initially, the parameter space is separated into 2 regions, depending on the sign of nu squared s. And strong electric phase transition occurs as a 2-step phase transition for mu squared positive via 3-level effects in the effect potential, or it can be a 1-step phase transition for mu squared positive due to the 1-loop 0 temperature corrections coming from the singlet sector. However, the physical parameter space for the 1-step phase transition is significantly reduced compared to the 2-step phase, to the physical parameter space of the 2-step phase transition. This is due to the following, to the previously mentioned constraints that we are going to describe further later. And yeah, you need to consider different constraints. So I'm going to focus on the 2-step phase transition, since the 1-step phase transition is not so phenomenologically rich. So we initially demand that the Higgs minimum is a global minimum of the effect potential at 0 temperature. And this imposes this constraint on the self-coupling constant of the single scalar field. And then I parameterize it in terms of a parameter A. And yeah, in the following, as I said, I will only consider a 2-step phase transition with mu squared positive. And we additionally demand that the 3-level potential is bounded from below, which leads to a Wilson coefficient, which is positive. Now, I see that I don't have so much time, so unfortunately, I will need to skip how the experimental constraints of the Higgs invisible decay width affect the physical parameter space. But here we have a bound on the Higgs singlet coupling, which significantly constrains the physical parameters. This is the physical parameter space. And so the blue region is the accepted physical parameter space by this constraint 12. So we see that the singlet scalar, the singlet extension is excluded for low singlet masses. It's almost excluded. And it's further excluded due to the Sphaleron rate criterion here that I showed here. So now we shall describe the behavior of the finite temperature effect potential further. And before that, it's important to understand that what we mean by a two-step phase transition. So we have an alternative thermal history of the universe where we start from a similar form of the effect potential. So the vacuum expression value is 0, but then we notice that there is the appearance of a minimum in the direction of the singlet scalar field, such that we have a phase transition, a phase transition in the direction of the singlet scalar field. And then, so we are here, we have, this is the critical temperature of the first phase transition. Then we have a local minimum. I see the time. I'm sorry for that. I will try to summarize everything. Yeah, so we see that there is a local minimum coming in the direction of the Higgs field. Oh, what happened? Atom. I'm sorry. And then, so the two vacua compete. There is so here it's not very visible, but the global minimum is described by the vacuum expression value of the single scalar field. And then, I'm sorry, here they are degenerate, here they compete. And the Higgs vacuum becomes the global one at the end. So we have a second phase transition, the second step in the phase transition in direction of the Higgs. This is I'm sorry, I don't see. Yeah, this is the physical parameter space in the high mass region, which is the region in which the singlet mass is higher than the half of the Higgs mass. But yeah, unfortunately, I won't have so much time to. The important point is to see that due to the presence, due to this Wilson coefficient, due to this dimension 6 operator, the ratio that determines whether the electroweak baryogenesis occurs is higher. So this particular singlet extension allows us to extend further the physical parameter space by increasing the ratio, this important ratio with respect to the Wilson coefficient. And yeah, here I discuss a little bit what happens for low singlet masses, which is a region of the physical parameter space that was completely exploded, and many people were not working on this extension because of this issue. And this also allows us to test experimentally this extension of the standard model. So by making this model valid for an electroweak baryogenesis. So here I summarize what I skipped. So a strong electroweak phase transition can be generated for low singlet masses. And in the Higgs resonance region, which is this region, a strong electroweak phase transition can be also generated for these values of the Wilson coefficient. No, for these ones. And the higher order parameter finally could assist a strong electric phase transition in regions of the parameter space that were excluded earlier in the literature. And the take-home message is that the electric phase transition in the Star model is not strong enough to generate the baryon symmetry in the universe, which motivates us to search for extensions to the Star model. And the simplest extension, in my opinion at least, is the simplest extension that can describe the baryon symmetry of the universe, describing a strong first-order phase transition. And I skipped this part, but you can also introduce additional sources of CP violation that can also satisfy the second condition of the Sakharov criteria. And an important comment, and last one, is that the gravitational waves from a first-order phase transition could be a message from the physics of the early universe. So the latest developments and the new detection methods in gravitational waves could help us verify experimentally the electric phase transition or other cosmological phase transitions, and understand deeply what is the physics